Hi there, my name is Dmitry and I welcome you on my technical channel. Here we talk about microcontrollers, big and small, and the ways of configuring and programming them. With this video, I'm starting a series of workshops dedicated to the system on crystal from Xilinx. Today, in my hands, I have a board called FreeRTOS, designed and manufactured by a company called Digilent. In the heart of the platform, there is a system on crystal, more specifically Zynq7020 from Xilinx, featuring 2 ARM cores and FPGA fabric. Next to it, there is a 512 MB dynamic RAM. Going to the peripherals, this is the USB host functionality, which we are going to talk in detail today. 2 HDMI connectors, one is syncing, one is sourcing. 2 P-mode connectors, which is a de facto standard for modern FPGA development boards. SPI connector, 4 tactile buttons with red LED on top of each other, 2 buttons with RGB LED on top of each other. There is a jumper that allows to choose to power the board either from USB port or from internal regulator. Reset button, DC power jack, mono audio output with amplifier on the board, 10 or 100 megabits per second or 1 gigabit per second Ethernet interface, and finally micro USB connector that combines JTAG and USB to serial interfaces. The 3-way jumper allows to boot either through JTAG, serial flash, or SD card. Also, there are connectors for Arduino-like shields. On the bottom side of the board, there is a serial flash and micro SD connector. Let's have a look at this board today and try to make use of its USB host functionality, specifically for FreeRTOS application. Some people may ask, why do we need USB host functionality in Baremetal when it is already available in Linux? Well, the problem with Linux is that it takes from 20 to 30 seconds to boot, which is not always acceptable by design. Imagine yourself working on a retro console, which interfaces with the USB keyboard, and it takes up to 30 seconds for the USB keyboard to come up. The next step you do is go and see at what comes with the board in terms of documentation and in terms of software support. You go to the official website from Digilent, look for the product, and then you can see there is plenty of information related to it. The product is even officially supported by the Xilinx Corporation, as you can see it on their own website. You look at the GitHub and there is plenty of repositories from Digilent, so you expect a lot of software support for the product, which is not the case. As soon as you start digging deeper, as soon as you start looking in the direction of FreeRTOS support, Baremetal, and board support packages, quickly you realize that there are big gaps in terms of driver support. One of them is a USB stack, which doesn't have support for USB host. There are ongoing discussions in the internet lasting for years, people complaining, everybody acknowledges and understands that there is no proper support. The library only provides a functionality for the USB device mode, but looks like nobody is even working on this. So in that sense, there is no There is no way we can enable USB stack as part of Baremetal application. Going back to the board, we can clearly see that it has USB Type-A connector, which is an indication that it can operate in host mode. Now, if we look at the schematic of the board, we can clearly see that the USB transceiver controls the power distribution switch, and it also controls a V-bus line. V-bus line is a property of a USB host device. So what it comes down to is that we clearly have hardware support for USB host operation. All we need to do is to find a USB stack already implemented by someone, or to open up a USB 2 specification and implement the whole stack from scratch. Obviously, the first option is much easier. We would need to integrate already existing stack with our piece of hardware and see how it goes. After doing a little bit of research, I found a potential candidate for our USB stack. It is called Tiny USB. It is hosted on GitHub. Has a lot of people working on it continuously. It is fully open source, obviously, has a MIT license, and the whole project was designed with cross-platform compatibility in mind. The only caveat is that it doesn't support Zynq's platform. So for us, it is going to be a challenge to integrate it with our hardware. I finally managed to address all the challenges and successfully integrated the tiny USB stack with Zynq hardware. I have a nicely packaged project, proof of concept, with the USB stack inside. Let's extract it and have a look. The project is subdivided into two parts, SDK and Vivado. Vivado contains a set of scripts and configuration files for PL side, programmable logic side. SDK contains C code and set of scripts for the application which is going to be running on ARM core. Let's try to build Vivado project and quickly go through the details of its implementation. But before I do so, I would like to justify the toolchain of my choice. I'm currently using Vivado 2017.3, which is relatively old. But it doesn't mean that it can't do the job. The biggest problem with Vivado product is that every single package suffers from multiple issues. And it is unreasonable to expect that the latest and greatest one is going to fulfill all your expectations. In that sense, Vivado 2017.3 is exactly what we need. It doesn't require gigabytes of hard drive space. It is proven to be working with the Zynq7000 platform. So why not to use it? But let's get back to our Vivado project. First, we need to create a project itself. We need to run a script, which is create project file. and it is going to take some time. So the project has been successfully created. Let's open it with Vivado IDE. Okay, the project is opened, and what we can see that it targets our board FreeRTOS. Let's open block design and quickly have a look at its configuration. As you can see, we have only one IP core, which is the minimum possible configuration of our hardware. Let's do double click and inspect interfaces. The most important one is going to be USB. We can see that USB 0 is enabled. This is exactly what we need. Ethernet interface is also enabled, but that's not very important for our proof of concept. Serial interface for the SD card is also enabled. SPI flash is also enabled. But most important one is UART0. So this is the interface that we're going to use for debugging for the console output. And some GPIO MIOs enabled as well. But let's check something else. There is a specific parameter which is also related to USB. And then we can see that USB reset is also enabled. And the USB reset is done via MIO 46. Let's check this configuration. We go back to the schematics. And we can see that the USB transceiver is getting reset by USB host reset N. Let's have a look how it is driven from the SOC. This is exactly the same net, and the name of this net is MIO 46. That corresponds to what we see in the Vivado configuration. So it means it is correctly configured. That's probably it. We don't need to do anything else. As you can see that DDR is also configured, but that configuration was transferred from the default settings of the board. So basically it was pre-configured by the Digilint, so we don't have to do anything else. What we're going to do now, we need to run synthesis, and see what happens. It will come up with 2 critical warnings, but to me it looks like there is something missing on the configuration side provided by the vendor. I think it is going to complain about 2 DDR lines and DDR memory. Well, if it is incorrectly configured, then it's not going to work at all. Well, we can demonstrate that it is working fine without any issues. Yes, it is something related to DDR clock delay, which we're going to ignore for now, especially taking into account that the synthesis process is still active. So hopefully it is not going to impact us. It takes a little bit of time to finish synthesis, even though we don't have much. Still, the process is not instantaneous. So yes, we have only one IP core, which is processing system. Nothing else is present, and there is the actual block design. So it means that the synthesis should take not so much time. Now it is running synthesis for the BD, which is the last step in the synthesis process, and it is finished. Synthesis complete, no errors. Now run the implementation, and this time I'm going to stop the video because it will take a few minutes to complete. Implementation successfully completed. Now we can open implemented design. But our next important step would be to generate bitstream. As you can see, the FPGA fabric is totally unused. This is because we're not really using any functionality on FPGA side. We only have the processing system in use. And this is also the reason why the implementation took so little time. The bitstream generation successfully completed. Now we can export the actual hardware and switch to SDK. Experiments, USB host, SDK, USB host. This is the place. And bitstream complete, it says. Let's have a look. Let's go into SDK folder, and yes, we have hardware configuration in the form of HDF file. So at this point, we can create an SDK project based on that HDF file. Let's do this. Create SDK. This process is potentially unstable. This is one of the reasons why Vivado package is prone to some kind of instabilities. It may work or it may fail, depending on our luck. But let's see without trying to predict anything. Looks like it didn't fail, which is a good sign. Let's wait for a couple of minutes until it completes. Looks like that the process successfully completed. Let's have a look at the actual files. FSBL ELF in debug and in release, yes. And yes, it successfully built everything. Let's open the project in SDK and I walk you through some of the peculiarities of it. Close the welcome page. No problems. Let's have a look at the project settings. And to be more specific, I'm talking about compiler symbols. Those are, the settings which are tiny USB specific. We explicitly say that we are going to operate in host mode. The target MCU is Zynq platform, and how we manage to do so, I'm gonna show you in a moment. The operating system is FreeRTOS. This is the way actually of telling the tiny USB that we're going to use blocking primitives and queues, for instance. This is a not very important parameter as far as I remember. And this is the way of enabling or disabling debug output. There are several levels of it. 0, debug output is disabled. 1, it is only reporting errors. 2 is reporting warnings, and 3 is reporting everything else plus info, as far as I remember. But we're going to test it again in a moment. Let's have a look at the project itself. So the main is relatively small, and I hope it is easy to understand. We have a couple of FreeRTOS specific declarations. This is the way how we handle static allocation for internal FreeRTOS needs. And basically we start an example thread. Let's go to the example thread. All it does, it initializes our USB stack, and then it handles events in an infinite loop, handles events from the stack. We hook up callback functions for HID driver. So in this example, we only activated HID driver to demonstrate the possibility of interfacing with USB keyboard. And this is a specific functionality, the functionality about HID keyboard class driver, basically. We also hook up to the callback functions to be notified when USB dongle is mounted and then when it is unmounted. And simply this is the function that handles our events coming from the callback function. So that's pretty much the whole demo. The actual USB stack is inside that folder. And let's switch to slightly different view. What I'm going to show you is what I have done in order to integrate the USB stack with our hardware. First of all, let's go back to the diagram. So this is the high-level view of the implementation of our application. There is a third-party library coming in the form of tiny USB stack, and there is a Zynq7000 glue logic, which I designed by myself, which is intermediate layer between the actual library and the USB hardware. There is also a separate link that allows us to interface with the external low power USB transceiver, and why we're doing so, I'm going to explain you in a moment. First of all, how I integrated the library itself. I added a new type of MCU, and this is the glue layer, which allows amalgamation of the library with our hardware. As you can see, it's not so much. There are callback functions for the events coming from the library. There is a specific case for our RT board and the low power stack, low power transceiver, sorry. This has something to do with VBus, and I believe that this is a potential issue of the transceiver itself, because looks like that it's not operating exactly up to the standard. Problem is that it has so-called VBus external bit in the register, which in addition to a standard one controls external VBus supply. In other words, if we don't forcefully set this bit, VBus external bit, to 1, then the VBus voltage never appears on the output of the transceiver. So we have to intervene in the process of configuration in order to write additional bit into a specific register inside of our USB transceiver. There is also one more challenge which prevents us from successful integration of the USB stack, but I'm not going to disclose it in this video. Instead, I would encourage you to go to our website and buy the library if you are interested, and then if you really need this project, then I suggest you to follow the link below this video, visit our website, and purchase our library. It's not very difficult to implement, but if you want to do it by yourself, you will need to go through all the pitfalls that we have gone through. You may find this time-consuming, you may not, but in the end it is up to you. So on this note, let's switch to the IDE, and let's try to run this proof of concept on a real hardware. Let's go to our board, and what I'm going to do, I'm going to connect a dongle from a wireless keyboard. And this is a very nice feature of the fully implemented USB stack, because now not only we can interface with wired keyboards, we can also interface with wireless keyboards. And the driver itself is not different from a wired keyboard, which is very nice, because you don't have to reverse engineer anything after this point. So let's apply power to the board. So hopefully you can see it now. Now let's switch to our project. Let's start terminal application. Way too many. All good. Let's create a configuration. Standard application. Reset entire system. Core 0. Not going to run FSBL, instead we're going to run our own application, and this is the debug version of it. And let's run it and see what happens. For some reasons it is going to rebuild the debug version of it. Okay, doesn't matter. It always does it. Remember me mentioning issues with Vivado? This is one of them. Uploading configuration. Now we take keyboard. Let me switch the camera. This is just an ordinary keyboard, and let me switch again, and let's type things 1 2 3 4 5 6 7 8 9 10. So as you can see, the keyboard is working. Now what we can do, I'd like to switch to debug output, more talkative. So if we do this, if we say 3, then in the console we should see much more information. Rebuild automatically. Successfully built. Let's run it. So now you can see all the packets coming back and forth from and to USB interface, which is really nice to debug. And then the keyboard is still working, and you can see the packets are coming every time when I hit a button, a key. So this is all I wanted to demonstrate you. Please like this video if you like it. Please go and visit our website. Please ask questions, and all the best. Stay tuned. Bye.